Welcome to The Explainer. We're diving into a technology built on rules so strange, even Einstein called them spooky. It promises to create unhackable networks, cure diseases, but it could also break every digital secret we have. This isn't science fiction anymore. This is the quantum revolution. To really get a handle on where we're going, let's start with a number that basically defines our modern world. 4.7 billion. That's how many people were online back in early 2020. And you know that number has only shot up since. Our entire connected civilization, every single email, every transaction, it's all built on a simple foundation of ones and zeros. But that foundation, it's about to get a massive rewrite. You see, the first quantum revolution gave us things like lasers and transistors, tools that used the effects of quantum mechanics. The second one is totally different. It's about grabbing the rule book of reality itself and learning to build with it directly. All right, here's how we're going to break this down. First, we'll get our heads around the mind-bending basics. Then we'll see how these things are actually being built. After that, we'll get into what it means for all of us, the good and the bad. And finally, we'll look at the massive global competition this has already kicked off.
So what really makes this a revolution? Well, it all comes down to controlling the quantum world directly and using properties that just have no parallel in our everyday lives.
At the very heart of this is the qubit. Now, the bits in your phone or laptop are like light switches, right? They're either on or off, a 1 or a 0. Simple. A qubit, though, it's more like a spinning coin. While that coin is in the air, it isn't heads or tails. It's kind of both. That state is called superposition, and it's what lets a quantum computer explore millions of possibilities all at the same time. Okay, so if superposition is weird, entanglement is where things get truly bizarre. Imagine you have a pair of gloves. You put one in a box and mail it to the other side of the planet. The very instant you open your box and see you have the left glove, you know, instantly, that the other box contains the right one. Entangled qubits are just like that. They are linked, their fates intertwined, no matter how much distance is between them. In fact, Albert Einstein himself was so baffled by this, he famously called it spooky action at a distance. He just couldn't quite accept it. And yet, here we are, decades later, and that very spookiness is the key to building the ultra-powerful, ultra-secure quantum networks of the future. So how in the world do you take these mind-bending ideas and turn them into an actual working machine? Well, that happens to be one of the single greatest engineering challenges of our time. You know, for years, the quantum race looked pretty simple. Whoever had the most qubits was winning. But the whole industry has hit this really crucial turning point. They've realized that a giant quantum computer that just makes mistakes all the time is, well, it's useless. So the new goal isn't just more qubits, it's better qubits. The focus has shifted from raw power to high fidelity, high quality precision. And this illustrates that challenge perfectly. On the left, you see just how incredibly complex a quantum photonic chip is. It's a beautiful, intricate piece of engineering. But as the data on the right shows, as you pack in more and more qubits, those pesky error rates can start to creep up. Solving that balancing act, that's the key to unlocking real quantum power.
And it turns out there's no single recipe for building one of these things. It's kind of like the early days of cars, you know? Some ran on steam, some on electricity, some on gas. Today, we have different approaches or modalities. Some companies use these supercooled circuits, others use lasers to trap individual atoms. Each one has its own pros and cons, and right now, the race is on to see which design is going to be the one to power the future.
Okay, so we're building the computers, but how do we get them to talk to each other? This is where we start weaving together the quantum internet, a network that can send quantum information from one place to another. And a huge breakthrough on this front just happened in Philadelphia. For the very first time, a team successfully sent these incredibly fragile quantum signals through the exact same commercial fiber-optic cables that carry our internet traffic every single day. Now here's the number that made everyone in the field sit up and pay attention. Over 97% fidelity. I mean, think about that for a second. Sending something as delicate as a quantum state through miles of regular city fiber and having it show up almost perfectly intact, that is a huge deal. It means we might not have to build a whole new internet from scratch. So how's it all put together? Well, a lot like the internet we already use. You know how today's internet has different layers? A physical layer, a network layer, an application layer that all handle different jobs? Researchers are designing the exact same thing for quantum, a protocol stack that will manage everything from creating entanglement down at the hardware level all the way up to running the apps that will change our world. Which brings us to the biggest question of all. So what? What does any of this actually mean for us? Well, this technology could solve some of humanity's greatest problems, and at the same time, create a brand new existential one. So on one hand, the promise is almost utopian. We're talking about designing life-saving drugs molecule by molecule, creating new materials from the ground up to solve our energy crisis, and optimizing global shipping and finance in ways we can't even imagine. And using the laws of physics themselves, we could create communication networks that are fundamentally, provably unhackable. But with all that incredible promise comes an equally great peril, a deadline that cybersecurity experts have a chilling name for: Q-Day. Q-Day is the hypothetical moment a powerful quantum computer boots up and renders pretty much all of our current encryption useless. In an instant, everything from your bank account to government secrets would be wide open. Now here's the crazy twist. The defense isn't some quantum shield. It's actually a new generation of much smarter, classical algorithms called post-quantum cryptography. It's a frantic global race to upgrade our digital locks before the ultimate quantum key is built. So you've got this dual promise of unprecedented power and an unprecedented threat. Well, you can probably guess what that's kicked off: an incredibly intense global race for quantum leadership, with nations pouring billions and billions of dollars into this. If you want just one snapshot of this race, look at the patent filings. As of 2024, the data shows China is way out in front in terms of sheer volume, holding a staggering 60% of all filings. The United States and Japan follow, but they're a distant second and third. And that patent race is backed by massive amounts of public money. China has announced it's investing over $15 billion. The US and European countries like Germany are also committing billions, launching huge national strategies like the US National Quantum Initiative and the European Quantum Flagship to try and coordinate all their efforts. But you can't just throw billions of dollars at a physics problem and expect a solution. Hardware is useless without the human minds to actually design it and run it, and that's the real bottleneck here. The true race isn't just for money or materials, it's for people. This has started a desperate global scramble to educate and recruit a whole new generation of quantum thinkers because demand for these skills is absolutely exploding. From some of the strangest ideas in physics to a full-blown global technology race, this second quantum revolution is set to completely redefine what's possible. The challenge for us now isn't just to build that future, but to make sure we're ready for the world it's going to create.